Okay, we will now go on with the agenda. And our next speaker is Ms. Barbara Rakovec Gorkic.
Yes.
From the Optomotive company.
Yes,
so,
correct.
Ms. Gorkic,
okay,
stage is yours.
Yes, thank you. I'm Barbara Rakovec Gorkic from Optomotive. We are actually building cameras that could be very similar to what Mirko Benz from Baumer presented. We use very large FPGAs for our cameras, but what we do is we also provide user programmable cameras. So not only that we customize cameras for our customers, but customers are also able to do that themselves if they have the capability of doing it. So we build also cameras with large FPGAs. And why we do that? Because the high-speed image processing beyond 100 gigabits per second is a big issue. So what I will be talking about is I will be talking about what to do when we have such a large amount of data that we need to process and that we need to put them through two bottlenecks. One is the bandwidth of the interface, and the other one is the bandwidth of the computer that is handling the vision software. So interface speed has been growing in past and is still growing today. 10 years ago, 1 gigabit GigaVision was a golden standard. 5 years ago, 5 gigabits per second with USB 3 were dominant. Today, 10 gigabit per second is a standard. 10 gigi is a standard, at least for automotive. And state-of-the-art for automotive and nowadays in general is 100 gigabits per second. So 100 gigi is becoming available. But currently, the fastest consumer off-the-shelf industrial imaging sensor features 21 megapixels at 1,000 frames per second. And this is a lot of data. This equals actually to 168 gigabits per second. And this is the bandwidth that we need. So here are some questions that we need to answer. One is price, performance justified? The ratio also. Why, where do we need such high speed? And what to do with all this data? Currently, there are several camera technologies on the market. Ethernet camera, PCI Express camera, Coax Express camera, Ethernet camera with integrated FPGA for image processing also. But let's not forget that at the end there is a PC, and on this PC a simple data copy operation hits a bottleneck at 15 gigabytes per second. So let's see these options, camera technology options that we have on the market today. So one of the most common ones is a 100G Ethernet camera with 200 gigabits per second, so dual 100G interface with a network card and with a server-grade PC with multi-core CPU or GPU processing. What are the pros in this case? This is a standard off-the-shelf equipment, so available easily. And network card can use RDMA to offload the PCU. The CPU, I'm sorry. What are the cons? 25G transceivers on camera side are expensive. The cost of network card and server-grade PC is high, as we need 16 lanes of PCI Express 4.0. Another con is also a huge number of cores and a lot of overhead for splitting tasks and combining results. And of course, long and expensive software development is needed to meet the required bandwidth. What about the PCI Express camera? This solution would be a camera with 16 PCI Express 4.0 that make together 556 gigabits per second. And they need to be combined with server-grade PC, again, with multi-core CPU or GPU processing. And the pros of such a configuration are direct link to CPU or GPU and memory. And the camera can use DMA for CPU offload. But there are more cons here when it comes to such a high data amount. Short, cumbersome, and expensive cabling is minimum 64 wires. High cost of networking equipment and server-grade PC. Again, the problem is huge number of cores, difficult and demanding development to meet the required bandwidth. Then there are coax express cameras on the market. And again, they need to be combined with server-grade PC, with multi-core CPU and GPU processing. And this solution would need 16 times 12 gigabits per second. So the pros are the low complexity on the camera side. And frame grabbers FPGA on the PC side can also be used for the image pre-processing. But cons are, again, cumbersome cabling. 16 coax express cables are needed. And at the end, there is no frame grabber on the market with 16 times 12 gigabits per second on coax express. So we at Optomotive, we believe that camera with large FPGA and 2 times 10 gig or 40 gig Ethernet is the right solution. Because on the other side, we can have a consumer PC with post-processing, and the camera side does the pre-processing. So as here are much more pros than cons, we will start with the cons first. So one of the cons is, in some cases, long and expensive FPGA image processing development. And the second one is a little bit higher cost for the camera itself. But the pros are many. It is the most suitable solution for pre-processing where the bandwidth is significantly reduced. These are applications, for instance, laser triangulation for high-speed 3D scanning, blob detection for motion capture, image compression, for example, RLE compression, JPEG compression, jet raw compression, probably some other compressions as well, image stacking, averaging, and so on. This system offers lowest total system cost, not to mention the length of the cable, which can be very, very long. And it offers also lowest latency and jitter. It is easiest way to match the required bandwidth. It connects with standard networking equipment, fiber and copper interfaces. And at last, but not least, the solution is scalable. For processing 2 times 512 bit pipeline is needed, which is 2 times 128 pixels in parallel running at 170 megahertz. So these are all the reasons why Optomotive believes in large FPGAs in cameras, and we only deal with large FPGAs and with cameras that are dealing with the full sensor speed in any case. So Optomotive's latest cameras are based on Xilinx Zinc UltraScape Plus system-on-chip FPGA. System-on-chip FPGA incorporates processing system and programmable logic into one silicon. Processing system runs Linux with communication stack for camera settings and data streaming, and programmable logic, which is a traditional FPGA. This part is used to capture and process data from the imaging sensor. So, best way to process image data in the FPGA is on-the-fly processing. This means that before processing, complete image is not buffered in external memory. This way, all data is processed at sensor speed with minimal and predictable processing delay. The data that comes out of programmable logic is buffered in the DDR4 and sent to host PC using DMAs. The good side of FPGAs is code portability, which is guaranteed. This means that the same FPGA code can be used across different FPGAs, families, and vendors. And it also means that the code you once have never becomes obsolete. You can reuse it on other cameras with other FPGAs. FPGA design can always be upgraded during entire camera lifetime. System deployment features can be added during camera lifetime through endless firmware upgrade possibilities. And if you don't have experience with FPGA programming, coding, it's no problem, because we know how to do it. Optomotive provides the complete solution with FPGA coding. The only thing we need from you is your algorithm, and we can also provide training for your engineers. So we offer user programmable FPGA cameras, but also we offer cameras from our standard portfolio and fully customized solutions for your applications. So Optomotive provides cameras for different applications. I will just mention 2 of them. One is probably the most accurate and the fastest confocal scanner on the market. It is also exposed here on the Vision Show. And the camera there forms, an Optomotive camera forms an essential part of this scanner. And Optomotive cameras with enhanced near-infrared sensors are used in motion capturing systems. They are a key component of probably one of the most widely used motion capture system for physiotherapy and sports. There are also other applications, but these 2 applications are also connected with the prior two presentations. So you've heard something from colleagues giving presentations before me. And if you have any questions, there's Dr. Ales Gorkic with me, who will be answering your more technical questions. I will thank you for listening to my presentation. And here's a big typo in my last slide. So it's not hall 8, it's hall 10, booth G11, where you can see our camera range portfolio and our customizable solution. So you are all very welcome on our booth to see how we deal with high-speed imaging sensors and with a large amount of data. Thank you.
Okay, thank you very much. Thank you very much for this very systematic presentation about the advantages of FPGA programmable cameras, especially when they are in automotive cameras. So it was very interesting to get this systematic overview. Thank you for that. And we are now going and have some time for questions.
There are no questions.
So that means, in general, that this was a very good presentation, because if there are no questions, everything was explained within the presentation.
I will be happy if you have questions to come and see our booth. So you're more than welcome. Thank you very much.
Okay.